Hi all, now we are going to discuss on the lighting design procedure, and here we are utilizing the zonal cavity method, and this is the most accurate method of lighting design. And the first step is to study the site plan, elevation of the installation, determine the lighting needs and consideration of the standards and the end user, select the light sources and luminaire, nature of the visual task and the energy criteria. So these are just preliminary thing before the lighting procedure, and once it is provided with the amount of lux level and the type of the lamps to be used, then we can go to the next step. So that is the calculating the ceiling, room and floor cavity ratios, and using table number 17 of the lighting handbook to find out the reflectance values. Okay, first we will be discussing about what is ceiling, floor and the room cavity. So this is nothing but the total height of the room, and this is the work plane, and therefore from the floor to the work plane is known as the floor cavity. Bottom of the fixture to the ceiling is known as the ceiling cavity, and the rest is the room cavity. So it is denoted by HCC, HRC and HFC, and the basic formula is 2.5 into H. H means whether it is a ceiling cavity ratio, room cavity ratio or floor cavity. So this H will be HCC for ceiling cavity ratio, H will be HRC for calculating room cavity ratio, and H is equal to HFC for finding the floor cavity ratio. Into perimeter. Perimeter is nothing but you have your room, length and breadth will be given. So it is 2 times L plus B will be the perimeter, and then area is nothing but L into B. Next is to find out the coefficient of utilization for the effective ceiling and the floor reflectances and the room cavity ratio. So that coefficient of utilization table will be given. This is for the floor cavity reflectance, it is given, and ceiling cavity reflectance is given here. Wall reflectance values are given, and then RCR is given, and from there you need to select the corresponding coefficient of utilization. Next is finding the light loss factor. L is given as maintenance factor, and for AC rooms it is 0.8, industrial environment it is 0.7, dusty areas it is 0.6. So this is again directly taken from your lighting handbook. And then as per the average lumen method we have already discussed in the previous lectures, it is area into illumination divided by coefficient of utilization into light loss factor into lumen output of the luminaire. You will be getting the total number of luminaires. Once it is done, then you need to arrange the fixtures. So the area per luminaire you can calculate it from room area divided by number of fixtures. The number of fixtures you are getting from here, and then fixture spacing or luminaire spacing is nothing but root of area per luminaire, and the spacing is to be that for high bay the spacing should not be more than the mounting height for high bay fixtures, that is in the case of godowns and all, and 1.5 times the mounting height for low bay fixtures. Low bay fixtures are nothing but what we are using in our domestic purposes. And if the spacing is too large, then you need to again go back to the first step, and then you need to change the wattage of the luminaire so that the luminaire output is less, and then you can do the calculations. Now we are moving on to the example. So here a classroom is given. It is 8 by 6.5 meter is the size of the room. Illumination level required is 300 lux. So if it is not given, then you can have to take it from the lighting handbook. The ceiling height is 4.5 meter. And the height of the work plane is 1 meter above the floor level. If it is not given, you have to assume it as 1 meter. And the ceiling, wall and fall floor reflectances are 70, 50 and 20%. You are asked to design a lighting scheme with a 2 into 40 watt. That is a double tube in a single fixture. That is what it is indicating, 2 into 40 watts. And the coefficient of utilization you need to calculate it from this particular table. And it is given that the luminaires are suspended at a height of 1 meter below the ceiling level. The light loss factor has to be assumed as 0.7. And it is also given that the spacing of the lamp shall not exceed the mounting height. And initial lamp lumen is 4000 lumens, which is given here. The first thing you need to find out is nothing but the cavity heights. From the ceiling, it is 1 meter. From the floor, the work plane is 1 meter given. And 4.5 meter is the total height of the room. So 4.5 minus 2, it is 2.5 meter is nothing but your room cavity. This is how the calculation is. So these two values are given and total height is given, and from there you are calculating the room cavity height. Once it is done, you need to find out the cavity ratios. So for finding the cavity ratios, first you are finding out the ceiling cavity ratio. So CCR is 2.5 into HCC. HCC is nothing but 1 meter. Into perimeter, that is 6.5 plus 8 into 2. You will be getting the total perimeter divided by 6.5 into 8 is nothing but the area. You are getting your ceiling cavity ratio is 1.4. So here floor cavity height is also 1 meter, and therefore ceiling cavity ratio and floor cavity ratio both are the same. Next is room cavity ratio. Cavity height is 2.5 meter. So you will be replacing H here as HRC, and you are getting the value of room cavity ratio is 3.48. So this is the preliminary calculations which is required in order to find out the reflectances values in order to calculate our coefficient of utilization. So this is the table number 17 which is taken from the data handbook, and here you need to find out the cavity reflectances in order to find out our room coefficient of utilization. So here this is, you need to consider it as a cavity ratio, not room cavity ratio. And this base reflectances, it can be ceiling or it can be floor. Okay, the first we are going to consider from the question it is given that the ceiling reflectance is 70, wall reflectance is 50. So here ceiling reflectance is 70 means first you are considering ceiling reflectance. So for 70, this is nothing but the 70 value. And from there, you need to consider the wall reflectance which is given as 50. And therefore that 50 is nothing but this one. So 70 and 50 is considered. And now we need to see that the cavity ratio of your ceiling is 1.4. So here you need to consider it as 1.4, and therefore corresponding to 70 and 50 and 1.4, the value of ceiling cavity reflectance is 55. So 55 is the ceiling cavity reflectance. So that was the value which we have found out. The next case, we will be finding out the floor reflectance, floor cavity reflectance. So here again it was given that 70, 50 and 20. So this was for the ceiling, this is for the wall, and this is for the floor. Again this is one. And now we are considering this as floor value. So the floor value is given as 20. So you need to consider the table for the value of 20 here, and then wall reflectance is 50. So you need to consider this as 50, and then 1.4 is your floor cavity ratio. So this is 1.4. So corresponding to 1.4 and 20 and 50, it is 18. So 18 is the floor cavity reflectance, and this you are assuming it as 20%. So that is how you are arriving at the values of the cavity reflectances. Next is you need to find out the coefficient of utilization. So this table is directly given from the question, and here two things are given. It is 20% effective floor cavity reflectance, and this is the effective ceiling cavity reflectances. So depending upon these two values which you have found out from the earlier slide, we need to calculate the RCR. So the floor we have calculated as 20% and ceiling it is calculated as 55%. So 55% means it is given it as 80 and 50%, and therefore the value of the ceiling cavity reflectance will be coming between 80 and 50, and therefore you need to give an interpolation. And the next one is the wall reflectance. Wall reflectance is given in the question it as 50%. So you need to consider these two things. Now our room cavity ratio RCR is 3.5. So therefore again we need to do an interpolation. For that we will be taking the values for 3 and 4. So for 3 and 4, for 50% it is 0.77 and 0.82, and similarly for 50% and 50% wall reflectance it is 0.71 and 0.74. These two things are taken it over here in order to find out the coefficient of utilization. And now you are having two different sets. One is for 4 and one is for 3. That is RCR 3 and RCR 4. You are having the coefficient of utilization values. So first you need to find out it for 55%. Which one? Your ceiling reflectances, because rest all values are given for our actual thing as 20%. So for 55% you need to find out for 4 and 3, and then you need to find out for 3.5. So first you need to find out for that 55% effective ceiling reflectance, and for that you are considering this particular set first. So it is 0.74 plus 0.82 minus 0.74 divided by, we had calculated for 80 and 50%. So it is 80 minus 50, it is nothing but 30, into this value was taken for 0.74 is for 50%, and you are calculating it for 55%. So it is, that difference is 5. So that you are getting it as 0.753. Similarly, for RCR is equal to 4, you need to calculate. So it is 0.71 is for 50% plus 0.77 minus 0.71 divided by, the difference is 80 minus 50 into, between 50 and 55 the difference is 5, you will be getting it as 0.72. Now you are coming up with this value as RCR as 3 for 0.753 and for 4 it is 0.72. Now you need to calculate it for RCR of 3.5. You need to find out a single value for your coefficient of utilization. You need to find out the value of coefficient of utilization. So in order to find the coefficient of utilization, we already have the table for 55% ceiling, 50% wall, and 20% floor reflectance. The values are 0.72 and 0.753 for 4 and 3. Therefore, for 3.5, obviously the value will be between 0.72 and 0.753. So therefore, that particular calculation you can do. Coefficient of utilization is 0.753 plus the difference is 0.72 753 minus 0.72 divided by 3 minus 4 into 0.5. So 3 minus 4 is minus 1, and therefore this will becoming negative. So that is what is seen over here. And you will be getting the answer as 0.7365. Now you need to calculate the total number of luminaires required formula. Area into 300 lux into divided by 0.7365 is nothing but the coefficient of utilization, and LLF is given in the question as 0.7, and therefore you are arriving at the number of luminaires. And again, the number of luminaires, it has to be an odd number, and therefore you consider it as 8 numbers, and it will be always taken as an even number. Now you need to see that whether the fixtures are fixed at a good spacing, and therefore you need to find out the area per luminaire or fixture, room area divided by number of fixtures. So 6.5 into 8 divided by 8, you are getting it as 6.5 meter square, and spacing between the fixtures is root of area, that is nothing but 2.55 meter. Now this 2.5 meter, it is said that mounting height is equal to 2.5 meter, and therefore the spacing should be below 1.5 into 2.5, which is equal to 3.75, and therefore whatever the spacing between the fixture 2.55 meter which you have obtained here is less than 3.75, and therefore your design calculation is correct. And in order to lay the luminaires, we can take out this particular formula. We can take x into y as 8 numbers, where 8 is nothing but the total number of luminaires, and you will be choosing x by y as the size of the room you are considering. So we can consider it as 8 divided by 6.5, that is equal to 1.23. You can solve for x and y, and you will be getting x as 4 and y as 2. That is 4 by 2 is the arrangement of your lighting fixture. So 4 numbers into 2. And you can equally lay the luminaires for a uniform illumination throughout your room. Now this is with a problem having given the cavity ratios and the wall reflectances, where you need to calculate the coefficient of utilization by yourself. And this question can also be directly asked just by giving the coefficient of utilization. So under such condition, only the parameters which will be given will be area will be given, lux level will be given, coefficient of utilization, LLF, and the lumen. You don't need to calculate the coefficient of utilization as in the previous case, because here coefficient of utilization is directly given to you for the reflectances which is being considered for that particular problem. So there you need to calculate the total number of fixtures. N will be equal to area into lux level divided by coefficient of utilization into LLF into lumen. You can directly apply this formula. You don't need to worry about how you're going to calculate the coefficient of utilization. That is when this kind of cavity ratios or cavity heights is not given to you. And from there, you can calculate the spacing, area per luminaire, and also the spacing between the fixtures. And that is how the entire problem related to the illumination system comes apart. Now, one more thing which we need to consider here is the glare, that is related to the quality of lighting. So the quality of lighting is related to the glare color rendering index and the modeling. So the glare, it can be of two types, direct glare and the indirect glare. Direct glare comes into picture with all tasks with head up position. Just imagine that you are going to view your light fixture which is fixed on the wall directly. Then whatever irritation which comes to your eyes or discomfort to your eyes is nothing but your direct glare, and it is in the task where the heads up position. And indirect glare is associated with a task that involves heads down position. That is, you are looking down to your work table and you are causing it is causing glare to your eyes while doing the task. That is the indirect glare. So you have your luminaire here, and this is your task surface, and you have your eyes here. Now you are looking onto your task or the work plane, and if you suffer any kind of glare, then that comes to be indirect glare. And if you are directly viewing to the luminaire, then it is a direct glare zone. So from 0 to 45 degrees, it is generally the indirect glare zone, because you are not looking with the heads in the up position. And from 45 to 90 degrees, you are at the heads up position, and therefore it is a direct glare zone. So the direct glare results from mainly two types of sources: excessively high luminous source staring into person's eyes. That is known as the disability glare. That is a high beam of an oncoming car. It is nothing but the disability glare. Another one is the discomfort glare. That is because of the peripheral stray lights that are not necessarily aimed at the eye. That is stray lights when you are doing some work. Then if because of the sunlight which comes through the window, it is affecting your vision, then it is going to be a discomfort glare. And the direct glare is measured in the factor of visual comfort probability. And the direct glare zone is between 45 and 90 degrees. So this is just showing the disability glare and the discomfort glare. Disability glare, then while you are looking directly to your luminaire, and discomfort glare is nothing but you are doing a work and through the window some light is coming and it is causing discomfort to your eyes, then that is a discomfort glare. Next one is the indirect glare. That is again result of the mirror effect of the task that reflects light from task to the eyes of the viewer. So you are having your on your work area, you are doing some work, and because of the type of the task, the light which is getting reflected onto the task and then coming to your eyes, then it is known as an indirect glare. So basically you can just imagine that you are keeping a mirror on your work table, and if the luminaire is directly falling light onto the mirror, then that light will be reflected back to your eyes. That is an indirect glare. So it is also known as wheeling reflection, and it is measured in terms of equivalent sphere illumination, and basically it comes in the degree of 0 to 45 degrees. So this is how you have your luminaire, you have your eyes with the heads down position. This is your work area. The light which is coming over here, if it is reflecting back to your eyes, then it is known as an indirect glare. So with this we are coming to an end of the lighting design for the interior systems, and the next section we will be discussing on the exterior lighting, that is referring to the road lighting. Thank you.